So yesterday we talked about percent composition, and we, silly people, and we discussed how that's how chemists would have represented what a compound was in the past before they had a knowledge of atoms and molecules and formula units and all that type of stuff. And it can be determined experimentally, all right? We can take a substance like magnesium. We're going to do this on Monday. We can burn that magnesium in oxygen. We can see how much the mass changes, and we can figure out exactly how much magnesium and how much oxygen is in that magnesium oxide. And with a very simple percentage calculation, what we want to learn about the mass of the magnesium over the total mass, we can determine the percentage of magnesium, and we can determine the percentage of oxygen. And so that's the way chemists years ago would have identified a substance. They would have identified it by percentages. And then at some point in time, they started to deal with masses, right? Historically, the masses were first determined by taking the masses of the compounds, the masses of the elements in the compound, and then dividing it by the smallest number, like hydrogen, in order to get relative masses, right? So what they were doing was every time they did an experiment, if it had hydrogen in it, they would take the mass of the hydrogen into the experiment, divide it by that same number, force it to be 1, because you're going to take that number divided by the same number, then all the rest of the masses you're going to divide by that hydrogen number. And what you're doing there is then you're getting the mass of all of the other elements with respect to hydrogen being 1. And that's how they originally started to get the masses of the elements. They had no idea that this was going to be a representation of the moles in the end, but they just had these masses. And once they had the mass numbers, they started to play around with the numbers. I'm sure some chemist was just fiddling with the percentage composition, looking at their mass numbers, starting to play around with it mathematically, and in the end, we get an interesting ratio. We get some ratio of the elements, not the ratio of the masses, but some kind of special ratio that was looking as if it was meaning something. And that's the beginning of our chemical formulas. What we're going to do today is we're going to use a combination of what they would have done along with what we know in terms of the masses to attempt to perform the same calculations that they did in order to get those first ratios of those first formulas, all right? So this is kind of like a little guide through what chemists would have done historically in order to determine those first formulas. And those first formulas would have been called empirical formulas. We've talked about the term empirical versus theoretical in this class already. What does it mean to be empirical? If it's an empirical definition, like the empirical definition of a compound, what did empirical mean? Yep. It's based on fact, not on theory. Excellent, that's correct. In terms of science and chemistry, fact is experimental evidence, right? It's everything we gather up in an experiment that we then have as experimental fact. That's correct. So an empirical formula, and this name comes from historical references. Empirical formula means it's a formula that was determined by experiment, not determined by theory. We know how to get a theoretical formula. We did that in that other unit where we learned how to do the crossover, because we used the theory of electrons and charges and oxidation states in order to determine a formula. That would be a theoretical formula, but we don't usually call it that. We just say it's the chemical formula, right? So the formula we're getting here is an empirical formula, a formula based on experiment, okay? Now, molecular formulas also come from empirical formula, but they deal with molecular substances, and there's a slight difference between the two. So I've told you where empirical formula comes from experiment, but it turns out that as time went on and chemists started to look at different empirical formula, they noticed that there was something that needed to be adjusted in the definition of an empirical formula. Would have been from experiment. That's a good definition. But when they started to look closer, the empirical formula started to behave a little differently than what we now call the molecular formula. First, let's compare and contrast those two terms, empirical versus molecular. So there's that first slide that many of you already have written down, and those who are writing quizzes are going to desperately try to get this down, but I'm going to probably advance it so quickly they're not going to have a chance. But that's okay. They can get it from someone else. So this one here gives us kind of a little add-on to the empirical formula. We now think of the empirical formula as the simplest whole number ratio. In other words, it's the formula with all of the common factors canceled out. It's got everything in lowest terms, the simplest ratios. Yes, it came from experiment, but now we know we must also consider it to be that formula where we've canceled any common factors away and we have the simplest formula. The empirical formula only indicates the types of atoms and their ratio, which are found in the entity. So the types and the ratio. They might not necessarily represent the actual number of atoms in that entity. We're going to find that for ionic compounds, the empirical formula is the proper formula. It's molecular compounds. It's the molecules that chemists eventually discovered that, wait a minute, chemistry's not as simple as we thought it was. We need to add an extra layer. So this next slide compares and contrasts some empirical formula with some with some molecular formula. I am going to want you to write this table down, but it doesn't have to be an official table. You know what I mean? You know how it works. Those of you who have your colored pens and your rulers nearby can make your table, and those of you who just want to make a table can do so. So chemists would have been starting to deal with their mass numbers. However, they were, obtaining those by finding, kind of ratios of masses. And they would have been mathematically playing around, and they would have come up with some of these numbers. They wouldn't even have probably called them formulas. They would have come up with H2O mathematically, and we'll describe where that comes from. They might not have known what it was, what they were looking about or talking about, because they might not have, known of the existence of atoms at the time. Actually, that's something I've never looked up historically. Usually I like to look up historically the order in which things have happened. I've never looked this up. I should. I guess my question is, what came first? The calculation of empirical formulas or Dalton's theory of atoms? It would be interesting to know whether they came up with the empirical formula first without even having knowledge of atoms, or whether as soon as Dalton proposed atoms, did someone say, wait a minute, that means if I do a neat little calculation, is this thing going to tell me about atoms? So to be honest, I don't know the order in which that came. That would be like a significant kind of thing to know. To you guys, it doesn't really matter, but, I guess it is kind of important. Let's not worry about it. Let's just assume they didn't know about atoms and they came up with these numbers. What they would have come up with from their calculation would be the simplest representation. In this case, water is in its simplest, lowest ratio form, which means the empirical formula for water is also H2O. It means that in each water molecule, there is 2 H's and 1 O, whether they knew about atoms or not. 2 something H's and 1 O. But for hydrogen peroxide, if they had done the calculations for that, because the empirical formula is only the simplest formula, when you do the calculation, you would have got a ratio of H to O. So chemists probably originally thought that hydrogen peroxide was just HO, because they didn't realize that it was 2 of those HO units together, stuck together, to make a proper molecule. So when chemists were looking at empirical formulas, they were not able to see the actual structure of the molecules. It was just the simplest. Carbon dioxide, if they would have done that for carbon dioxide, they would have seen CO2. It's in its lowest ratio. Now something like octane, and here's where the wheels kind of fell off for the chemists, where they realized probably that chemistry was far more complex than they thought. If you actually, the wheels would have fallen off down here. Let's do the octane one. What can I reduce that to? What can I, Janessa, what do you got? C4H what? 9, is it? Yep, thank you. C4H9. It's my hearing, and I thought you said 5, and that didn't make any sense. But no, that's great. Divide off a common factor. That's the simplest version of it. Again, this is actually made up of 2 units of that stuck together. Here's where the wheels would have fallen off for the chemist. What would the simplest ratio be for this one, Atlee? CH. And how about benzene? What's the simplest ratio for that? CH. All right. Up to that point, not necessarily, it wasn't necessarily with ethine and benzene that they would have done this with. There's all kinds of other molecules that this would be an example of. But at this point, they would have figured that the percentage composition indicates what the substance is, but obviously for these 2 molecules, their percentage composition would be the same. We would take the C and the H and find the percentages, and therefore 2 completely different molecules with completely different properties would have the same percent composition. So then chemists are going, okay, now we've got an issue. Again, they would have had the same empirical formula, and therefore that forced chemists to start thinking about, wait a minute, so what's going on in here? What's happening in that molecule to make these 2 different? All right? So the molecular formula is representing the entire molecule, and the empirical formula, you don't have to write that down, it's just a statement, and the empirical formula represents the simplest. Ethine and benzene will have the same percentage composition since they have the same empirical formula, and so to a chemist of 300 years ago, they wouldn't be able to distinguish between those 2 except knowing that their properties were different. Now, one statement before we start doing the questions, and I do want you to write this down. Due to the fact that we already cancel out common factors for ionic compounds, their empirical formula is their final formula. It's only for the molecules that we've got these troubles. Now those questions there simply ask you very simple qualitative questions about the difference between an empirical and molecular formula. They don't tell you how to calculate it. They don't ask you to do anything complex like that. So those questions just ask you to distinguish between empirical and molecular. I'm not going to let you work on them. We're now going to go on and do some calculations. Then I'll give you some practice problems, and then you can go and work on them. So empirical formula, the simplest. For ionic compounds, the empirical formula tells us the formula. for molecular compounds, sometimes the empirical formula tells us the formula, but sometimes the empirical formula isn't enough. We need a little more information. My plan is that today I teach you how to just solve for the empirical formula problems, and then on Monday we deal with what to do if it's a molecule. We'll break it into 2 steps, but really they're 2 parts of the same process. So today we're only going to deal with how do we figure out that empirical formula, that simplest formula. And really it's just, hold on one second. Don't write that stuff down. What am I doing here? Let's jump ahead here. Yeah, no, we're not going to write all that stuff down. We're going to go straight to an example, but let's back up first. Back up to there. Back up to there. I'm back here. Well, yeah. Let's stop and think about a formula first. Not a molecular formula, but just an empirical formula. Let's stop and think about what something like, we will do Al2S3. Let's just look at that, aluminum sulfide. And let's talk about what the 2 and the 3 in aluminum sulfide really represents. And I'm recording this, so I'll write it on here. Al2S3. What do those numbers really mean? You tell me. What do those numbers in Al2S3 stand for? So that we can get a plan on how to solve and find those numbers. All right? What do they mean there, Brennan? Excellent. This is 2 Al atoms and 3 sulfur atoms. In the end, they become ions, right? But you're right. If we're counting atoms, that's correct. And that's a good interpretation of it. But it's a real pain to calculate for atoms. If we're going to do some calculations and we eventually want to solve for those numbers, because that's what we want to find, dealing with atoms is really a pain because they have a mass in U and we don't want to deal with U anymore. It's way too small. So I've introduced you to a new interpretation. We don't have to deal in atoms anymore. What else could this be considered when looking at the 2 and the 3 instead of atoms? Yep. Yeah. If we had a mole of that stuff, it means that we would have 2 moles of Al and 3 moles of S. Does that make sense? Because moles is essentially supersizing it. Whether we talk about individual atoms or a mole of them, it doesn't make any difference. It's like if I talk about individual cobs of corn or a dozen cobs of corn. A dozen cobs of corn, can I say that? No. A dozen, I guess I can. Let's not worry about the English. So if we can somehow figure out how many moles of a particular element there is in a substance and how many moles of that other element there is in that substance, then we essentially have the empirical formula of that substance. We have the empirical formula for a mole of that substance, which then we can shrink back down and talk about them in terms of atoms. So that's what we want to do when dealing with empirical formula. We ultimately want to figure out how many moles of that stuff that we have. This next slide talks about what it really stands for, atoms and moles, blah, blah, blah. We're not worried about it. This involves a bunch of rules that we need to do in order to kind of solve these problems. I'm not going to write that down. I'm going to jot down the rules as we do a problem. If you want to go back to the slide online, you can always go back and read the steps, but I don't think this is useful. And let's then jump right into an example. Now, this example, and we will have 2 types here again, one that starts with a percentage and one that starts from experimental data. These are examples where we start with a percent. Start with percent composition. So these are examples where we're going to be starting with a percent composition. And then we're going to do a couple of examples where we start with experimental data. So very much like yesterday, you know what we're doing? We're doing yesterday's work in reverse. We started with a formula and we found a percentage composition. Here, we're starting with percentage composition and we're going back to get the formula. So that's essentially what we're doing. We're reversing the process of yesterday. Ultimately, I need to find moles. I need to find how many moles of sodium are in this thing, how many moles of chlorine are in this thing, and how many moles of oxygen. And I'm not talking about chlorine gas. I'm talking about chlorine atoms, right? That's what that number represents in the formula. I cannot take a percentage and turn it into moles because I don't have a conversion factor that converts percent into moles. What can I turn into moles? What can I start with and end up with moles? Because that's what I need. I can start with entities, but those are back to the atoms. We don't want to deal with atoms. They're way too small. What else can I convert there? Grams. So if I'm starting with a mass, then I could convert that to moles. If I'm given a percentage and I assume that I have 100 grams of that substance, then it's going to be very easy to determine how many grams of substance I have. So if I make an assumption, okay, I've got 100 grams of this stuff, then in terms of Na, what mass am I starting with? Yep, 21.6. I turn the percentage into grams, right? So that's the first step we have to do. 21.6 grams. I'm going to do it for everybody here. Cl is going to be 33.3 grams, and O is going to be 45.1 grams. Excellent. We're on our way now. In that sample of substance, there are those grams of that substance. What do I eventually need to find? Moles. How am I going to turn my grams of sodium into moles of sodium? How do I turn mass into moles? We're slowly losing it, but that's correct. I'm talking about just sodium, sodium atoms. Can somebody please find that information for me? I don't think I need to write it down off the side. We're talking about one atom here. I just need to get the number. 23.0, what's the unit that goes with that? Nope. Grams per mole. Maybe we do need to write it out. We'll do it once. Na 23.0 grams per mole. What's going in where so I can convert that 21.6 grams into moles of sodium? What goes where? Yep. 1 mole on the top. 23.0 grams on the bottom equals, and you will do the exact same thing for the rest of the elements using their molar masses. What's the molar mass of chlorine? Have we found it? 35.5 grams. And 1 mole mass of an oxygen? Yeah, 16.0. Hopefully we've got that one memorized. And now you're going to come up with 3 numbers. And I will take those numbers to 3 significant digits, please, when you have them. Yeah, Chelsea? That's okay. It's not significant. It's a placeholder. 939 moles. And I'll take them as they come in. Yep. 938 moles. And? Yep. 2.82. 2.82 moles. And we said that the purpose of finding the empirical formula was to determine the moles, and we've done it. That means the formula of this is Na 0.939, Cl 0.938, and O 2.82. There you go. There's the formula right there. What's that? It's a really odd formula. I've got decimals all over the place. Is that acceptable? No, that's not an acceptable formula. Concern, sir? Anybody else at 0.941? No, I didn't think so. You've entered something incorrectly. I guarantee it. Okay, now, is that an acceptable formula? No. What has to be true about the numbers in a chemical formula? They have to be whole numbers. So this ratio is fine. We just got to somehow squeeze these into whole numbers. We need to turn them into a whole number ratio. How can we do that? How could we do that? How could we turn something that looks kind of goofy into whole number ratios? And by the way, these lowest numbers, what number do you think they have to be? They've got to be ones. How can I turn a number like 0.939 into the number 1? What do I do mathematically? Put it in a fraction. I need a little more guidance. I'm sorry. That was fun. It's like voice text recognition here. Yep. Yeah, that's correct. That would do it. But there's an easier way to express that. What if we just took the number 0.939 and divided it by itself? Right? And because, actually, we have to use the smallest number because we want to represent everything with respect to the smallest number. Or sorry, 938. Now don't write this stuff down because I'm going to show you the calculation we're going to do here. But if I take this divided by this, what's that essentially going to be equal to? 3. That's 1. Na1. This one? 1. And could somebody run this through a calculator? We're getting 3 there? What do you get as a number? 3.00, so the 3. That's a successful empirical formula. So what we do is we take those ratio of the moles, divide by the smallest number to squeeze everything into a ratio with respect to that. This thing is NaClO3. What is that stuff? We have a name for that stuff. Yep. It's sodium chlorate. So on your calculation, here's the next calculation to do. Once you get these numbers, divide each of them by the lowest number. One, 1, 3, 1, 1, 3. And therefore, the empirical formula, and I just write it as EF, is Na1Cl1O3. We simply take the molar mass, convert the mass into the moles, we divide by the smallest number to make it into a whole number ratio. All right? So if we're writing rules, we're assuming 100 grams. Here in step number 2, we convert to moles using the molar mass. And here in step number 3, we divide by the smallest to get a whole number ratio. It's better than writing all that whole page down. That's essentially what you have to do. If it's a percentage, you assume 100 grams. You then convert it into moles. You then divide by the smallest number to get a whole number ratio. And then you've got it. Let's do a couple more examples. Pausing for those little notes. Do we have them? We got them? All right, let's do another one. Now again, hopefully you've got your pencil. You can kind of move on ahead of me. You're going to find, though, after you divide by the smallest number, you're going to have a little issue on this one, and I'm going to address that little issue. There's a little bit of a hiccup that exists for some of these empirical formulas that we have to deal with. Yes? Yeah, you don't even have to write that down. You get a percentage one, just write the mass in grams and go. The assume 100 grams is really step one. I don't need to see you write it down. So if I'm looking at this question and I'm in a hurry on my test, I see the percentage, I am writing NA 17.6 grams, CR 39.7 grams. What did I just do? O, and that is 42.7 grams. Biggest thing is you associate the right atom with the right masses. If you don't, it falls to pieces. At this point, you're just getting molar masses. You don't need to tell me or write down, right? They're all going to be 1 mole over whatever the mass is. You don't need to write down Na, arrow, right? We just need the molar mass. I think we just did that one. What was it, 23.0? 23.0 grams. Oxygen is 16.0 grams. Chromium, 52.0. 52.0 grams. Now you got the calculators flying, and you're finding the number of moles of each of these things, and they're not going to be pretty, which is fine. And I will take those 3 significant digit numbers when you get them. Yep, what do you got there? 765. Yep. 763. And we're not worried about that. That could be some kind of little, random error in the experiment itself. Not a problem, but that's looking like they're the same. That's looking 1 to 1. And the last one. Yep. 2.67, 2.67. So now we're dividing off 0.765 divided by 0.763. And you know what? I'm just writing down 1 there. Even though it's not exactly 1, that's close enough. 0.763 over 0.763. That's a 1. 2.67 over 0.763. And I'm not sure. What do we get there? Yep. 3.5, you guessed. That's excellent. You can potentially have a 0.5 at that location in the question. 3.5. Now, what you're saying is, hey, I can't have a 0.5 in there. That's correct. We're not going to worry about that at this point. We'll deal with it in a second. What that means is these others actually aren't a 1. This is a formula that doesn't contain any 1s in it. It contains other numbers. And so its lowest ratio doesn't contain 1s. It does have the ratio of 1 to 1 to 3.5, but we know what to do when we're dealing with a 0.5. It's like in a balanced chemical equation. If I get a 0.5, how am I going to fix this problem? I'm going to double everything. So I'm going to write a little note here off to the side. If, all right, I could have used a different color. I didn't. If you get an x 0.5, and when I say x 0.5, I mean like a 1.5 or a 2.5. You get the idea, right? How do you fix it? You multiply by 2. I shouldn't have used x because I'm going to put here times 2. That's a littler x than that x. Double? You mean writing all those letters down for that double? Oh man, I'm not doing that. Spelled it wrong. Sometimes you can end up with an x point, now I got to think here, 33. Sometimes you can end up with an x 0.33. How would I get rid of an x 0.33? Yep, times it by 3. It's going to make it into a whole number, times by 3. Sometimes you can end up with an x 0.25. Yeah, times by 4. We're starting to see the trend here. Sometimes you can end up with an x 0.2. Those are really tricky because you start making mistakes between whether it's a 2, 5, or a 2. What am I doing with this? Multiplying it by 5. I'll tell you right now that there's an example that you will do. You'll end up with an x.66. But a 0.66, you treat like it's a 0.33. Multiplying it by 3 will get rid of that, right? It's like a 0.5 with a 0.333 on it, right? So, well, no, it's not. It's 2.33s. So you can triple it as well. All right. So in this case, I'm doubling everything. Times 2, times 2, times 2. That's even the way I write it. I just slap a times 2 on the back end. And now I can write the empirical formula. Somebody tell me, Na2CR2O7. And that is, I think that's a dichromate. I think it's a sodium dichromate or something like that. All right? So a little add-on to this question. You can end up with a 0.5 here. If you end up with something like a 2.17 at that location, then you conclude you've made a mistake. And you go back and you check your molar masses, make sure you've got the right one, check to see that you've transposed the information from the question down into the right location. But if you end up with a 0.5 or these guys here, you're okay. You can multiply to get rid of it. Okay, let's do another example. And then we will do an example that deals with experimental data instead of the percentages. Okay, this is one then that you should be able to do all by yourself, because I've dealt with all the pitfalls. Remember, we're dealing with atoms, eh? 1 gram. We're not dealing with O2s or H2s. They're just atoms. I will take those numbers as they are being calculated. Yep, go ahead. 3.33. 3.33 again. That's kind of nice. It makes us feel good. Oh, 6, I could have probably figured it out. 6.7. 3.33 divided by 3.33. 3.33 divided by 3.33. Some people say, do we have to actually write that down? You do. I need to see you generate that ratio, all right? And 6.7 divided by 3.33, and I got the first 2, and the last one, yep, Rody? Just 2, straight up 2? Excellent. So no need for any extra factors. COH2. Usually we write the H's second. It doesn't matter. CH2O. It doesn't make any difference for you guys here at this point, but as you continue with chemistry, you'll find that we tend to put the H's and then the O's on the end. Excellent. There's the empirical formula. Any questions or concerns on determining the empirical formula? Okay, now that's starting from percentages. The next examples deal with starting from experimental information. This is actually number 26 on this sheet here. so you don't have to actually write it down if you'd like. Just write down number 26 on the worksheet, and I'm going to hand the worksheet out in a moment. So if you want to make reference back to that question when you're studying, it's right here. You don't need to write it down. It is easier when dealing with experimental data. With experimental data, they simply didn't turn it into a percentage. We could turn this question into a percent composition. We could figure out the total mass by adding the three together and then doing a regular percentage calculation. But it doesn't matter because in the end, I've got to turn my percentages back into masses. So why would you take masses, turn them into percentages, and then turn them back into masses? So when you're given experimental data, you can just start right out with the mass. It may not add up to 100. That's because it wasn't turned into a percentage, but that doesn't matter. So this is easier. There's less thinking. I take my mass of potassium. I take my mass of sulfur. I take the mass of oxygen. And I don't care that the sample doesn't add up to 100 grams. It is what it is, and I complete the calculation. So when dealing with experimental data, easier. There's no thinking involved. Take the masses and turn them into moles. So go ahead. You can finish this one off. Now the process is exactly the same. Figuring out how many moles of potassium, how many moles of sulfur, how many moles of oxygen, and I don't know those other masses. 32.1 for sulfur, looks like. And heading over to the K, potassium, 39.1. 39.1. I will take the moles when you get them. You've calculated them. Yep, Brody, what do you got? We want 3, because again, our molar masses are going to limit us to 3. 459 moles. Jory, what do you got? Did you say 229? 229 moles. Yep. 0.919 moles. Dividing by the smallest. 0.229, 0.229, 0.459, 0.229, 0.919, 0.229. I got the middle one. It's 1. I'm hoping this guy's 2. Yep, 2. And I'm not sure what I'm going to get for this one. Yep. 4, right on the money, 4. Like, not right on the money, but 4.0 something. Yep. So no need to do a double or a triple. That's fine. All right, so that's good. We've got the empirical formula. And that is K2SO4. Hey, we recognize that one. What's that stuff? That's potassium sulfate that they must have been analyzing. That is the empirical formula. Not too bad. It's using our mole tools, but we're essentially figuring out how many moles are in the formula of a substance. In terms of practice problems, I'm not doing another example. In terms of practice problems, there's a few of them out of the textbook. All right, and then I have this worksheet which came out of a book that has all kinds of different examples, and the first bunch of them are percentage ones, and the next bunch of them are starting from masses, and I do have the answers to this up online in that solutions folder. It'll be the empirical formula extra practice sheet. You might think this is very repetitive and almost easy, but I do suggest you try some of these. They've got some of those trick ones in there with some 0.25s and some 0.33s, and it gives you some practice looking at those guys. All right?